this will be another one where we aren't given an explicit domain. So we'll have to figure it out ourselves. Okay, so what we're supposed to do is the following. The directions are find volume of solid, well, I'll put the solid. Okay, hold on. Of the solid in the first octant. Bounded by, and I'll give you some equations here. We have x plus y plus z equals 1, and x plus y plus 2z equals 1. Okay, so this is all of the information they give us, and I think they might also give you, if you've never seen the word octant before, that's kind of like in 2 dimensions, you think of quadrants, right? First quadrant, second quadrant, third, and fourth. But in 3-dimensional space, then you have 8 octants, because then you have the 4, it's kind of like cubes, like 8 cubes formed. Anyways, so the first octant is just characterized by everything being positive. So x is positive, y is positive, and z is positive. Okay. So automatically that gives us some pieces of the puzzle to the bounds, right? Because now we know that all of them have to remain positive, so that's good. And these equations here, you can recognize these as planes, equations of the planes. But anyways, so what we're going to have to do here is get z's by themselves, okay? It's kind of a standard rule because we want to find our z1 and z2, right? So z whatever, I haven't labeled them 1 or 2 yet, but we'll see. So z here on the left equals 1 minus x minus y, and z on the right, this equation turns into 1 minus x minus y over 2, all right? And yeah, okay. So what we're going to do here is, because we have x and y as being positive, right? So when x and y are positive, then, like, let's say we plug in some point. Let's say we're going to do x equals, well, we can't do 1/2 and 1/2 because then that would be 0 and 0, and that would be inconclusive. But we can do like x equals 1 and y equals 1, maybe. Okay, backing up. Actually, let's just think of this as we do know that we're in the first octant, which means all of the x, y, and z values are positive. So when x and y, that means that z's are going to be positive, right? So we can tell which one's the greater one because these are both going to be positive values, and one of them is simply half of the other. So this is going to be the lower one. So this is lower, so this is going to be our z1 of xy. That's a comma, sorry. And this is going to be the upper one, right? The higher one. So this is going to be our z2 of x and y. All right? And then, like I said before, we don't have an explicit domain. It's not given to us. So we're going to have to find it. So find D by finding intersection between the two surfaces. By finding intersection of the two surfaces. Okay, so we're just going to simply set one equal to the other. Minus x minus y over 2. And we'll just multiply times 2 on each side. 1 minus x minus y. And when we rearrange this, I'm going to subtract a 1 over and add these values to make them all positive. So when we do this, these cancel out, those cancel out, and on the left we have a 1 equals a positive x plus positive y. Okay? And so this intersection, these two planes basically intersect in a line, right? This is the equation of a line. So I'll take this and I'll show you what it looks like on the next slide. So we have y equals 1 minus x. So that would be the line described by The y-intercept is 1, and it has a slope of -1. So it'll intersect here at 1 as well. I should write that separate place. Okay, I'll be lucky if these actually make it through the point, if this line actually makes it through. Okay, so it looks like that. And now you might be thinking like, but is it on the right side or the left side, or where are the bounds? But this, remember in the beginning that we said x has to be greater than 0, equal or greater than 0, y is equal to or greater than 0, and z is equal to or greater than 0. So basically, we have to be in the first quadrant here on the two-dimensional xy plane. So that means that x is always going to be positive, so to the right. So it'll be over here, and bounded by this, well, x is, okay, yeah. So we're not concerned with x really. Well, we are, because it has to stay on the right side of this line, and y has to be positive. It can't fall into the negative, so it has to be bounded here as well. So our domain is essentially this triangle. So that's our D, and so we found that this is the equation of the line, right? So this is y equals 1 minus x. So this is the top bound for our y. Okay, this equation here, that is what is bounding y on the top. And what's bounding it on the bottom is 0, right? Because we have to stay in the positives. And the bounds for x are pretty simple. They're just from 0 to 1. Because I'm thinking this is horizontally simple. Vertically simple. I made a little mistake there. Vertically simple, right? Because we're drawing vertical lines. You could likewise do it horizontally simple, because it is. If you want to switch that around and then say that x equals 1 minus y, you could do that as well, and then use the fact that y goes from 0 to 1. But I'm just choosing it this way. So this is the vertically simple orientation, or not even orientation, just the method, vertically simple. Okay, and then this way, on the other hand, just to review, would be horizontally simple. And then the same thing. Okay, so now that we have our bounds, we're ready to go, except for we aren't given an f of x, y, z, right? So that's kind of a problem. But if we look back, or if we think back to the question, it told us find volume. Okay, and remember, if you watched the concepts video, I mentioned that whenever you see something about volume and you're doing something with a triple integral, this should trigger you to think that of the special case, right, when f of x, y, z equals 1, right? So when this happens, the triple integral over a given region and our function equaling 1 will give you the volume. Whatever answer you get is actually the volume of W. Okay, so that's what we're going to make use of in this case. So we're just going to make our f of x, y, z equal 1, because they didn't give us 1, so there's no limitations on it really. Okay, and then we have our bounds, so we'll set it up on the next slide. So we have our simplest bounds, 0 to 1, and this is for dx. Okay, and then our next simplest bounds, I guess, would be the y ones, going from 0 to 1 minus x, so that's dy. And then we have z bounds, which are from the lower one, so that would be 1 minus x minus y over 2, all the way to 1 minus x minus y. And then this is dz, those are our z bounds, and our f of x, y, z is 1. Okay, so now we can start solving. These bounds look a little bit messy. They'll work out in the end. Okay, so looking at the inside, we're just going to start integrating here. 0 to 1 minus x. And then on the inside, we have a z, as z goes from 1 minus x minus y over 2 up to 1 minus x minus y. And this is dy dx. Alright, so let's plug these in. Okay, 0 to 1 minus x. And we're going to get 1 minus x minus y minus 1 minus x minus y over 2. Okay, and we can just pretty easily simplify this because it's like think of this as it's just one quantity of something. So it's like there's a 1 in front here minus 1/2 of that thing. So that'll just be a positive 1/2 of whatever we have. So essentially what we're going to get is a positive 1/2 of 1 minus x minus y. Okay? And at this point, I just want to bring the 1/2 outside here. It can just hang out in front. Okay. So we get 1/2, 0 to 1, 0 to 1 minus x. And then on the inside, we have 1 minus x minus y, dy dx. So now we'll move on to the next step and integrate with respect to y, holding x as constant. So then we have 1/2, 0 to 1. Woo, that was a weird one. Okay, and then we have a y minus xy minus 1/2 y squared. And this is evaluating from y equals 0 up to y equals 1 minus x. And we have a dx, okay? And then we'll just plug in these values. So what we get is 0 to 1, a 1 minus x times 1 minus x minus 1/2 1 minus x squared. And then all of these terms contain a y, so that means when you plug in 0, it's just going to turn out to be 0. And then we have dx here. Okay, so I'll continue on the next slide. So what we get is, I'll just simplify a little bit, step by step here. So 1 minus x plus x squared, and then we get a minus 1/2 times 1 minus 2x plus x squared dx. So as you see here, we can simplify a little bit, and this actually works out nicely, well, relatively nicely. So we get a, I'm just going to, 1 minus 2x plus x squared minus 1/2 of, if you realize that is the exact same thing that's here, right, in parentheses. So what this is like a 1 something minus 1/2 of that something. So this will turn out to be a positive 1/2 of that something in parentheses. Okay, and I'm just going to combine these two. So we get a 1/4, 0 to 1. And here again, I'm just switching them around because I like to do descending powers. Okay, so this is what we have, and we're down to single variable calculus, and we can just solve pretty directly. 1/3 x to the third minus x squared plus x, as x goes from 0 up to 1. Okay? Alright, so now we can just plug them in. And we get 1/4 times 1/3 minus 1 squared minus 1. Okay, so these cancel, and then we have a minus 0, of course. And this turns out to be positive 1/12. All right? So that finishes it up for that problem. And that's all I had for you. I just wanted to show you a couple different examples. And I hope that helped. And good luck on the rest of your homework if you have not finished already. And if you finished, then great. I would suggest doing some more practice problems. But, okay, you can never get enough experience, you know. It always helps to continue doing problems. All right, so I'll talk to you in the next video if you watch.